All right, so in this lesson 6.2 average value, our goal here, our objective is to find the average value of a function. Now, of course, functions, continuous functions anyway, have an infinite number of values, so calculus gives us a way to take the average of an infinite number of values, and it's an application, as we're about to see, of an integral. In this particular lesson, after we're done with this particular lesson and your assignment, if you look over here on the right-hand side, you can notice that there is a homework supplement that's tied to it. This homework supplement has some, I think it's free response questions from College Board. All right, so let's take a look with speaking of a free response question, warm-up question here. We've got a table of values. This is one of those tabular kind of problems, contextual problems. Hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup at time t between 0 and 6 is given by a differentiable function c, where t is measured in minutes. Select values of c of t, measured in ounces, are given in the table above. All right, that's what we see. That's what's presented to us. The actual question here is asking us to find the average amount of coffee in the cup for the 6 minutes indicated by the table. Well, we know that, hey, if I'm going to find an average value of something, I'm going to add up however many values I have and divide by, in this case, I should be dividing by 6. So let's take a look at this. So what I would be doing here is just, I'm not going to include the 0 here, and you'll see why I'm not going to do that in the next part of this lesson here. I'm just going to take the average of these. And to take the average of those, obviously, I'm just going to add up I'm going to average the y values here. It's 5.3, 8.8, 11.2, 12.8, 13.8, 14.5, and divide this thing by 6, right? And if I'm not mistaken, this was a calculator active question, so I will pull up my calculator application here. And I've already typed it in here because nothing more boring than just watching somebody type something into the calculator, especially something as long as this. That's right, nothing more boring. All right, hit enter. I'm actually going to hold and enter so I can approximate this value here. Now, if you have chosen to use this app, this is the TI Inspire app, you might need to, right up here under settings, document settings and display digits, it usually defaults to float 6. I'm going to float period, and it's going to show me all the decimals that it possibly can here. Go back to document settings and hit done, and there we go. And then, of course, for the purposes of the AP exam, they want us to record just 3 decimal places. So this is 11.067. And then as far as the units goes, this is in ounces, and yeah, it's in ounces. All we did was we added up each thing that's down here at the bottom, which is in ounces. Average number of ounces in the cup over that time interval. Okay, so this actually wasn't the question, right? The question was this. Use a right Riemann sum indicated by, I've given you a sneak peek of what the thing is supposed to look like. You're not supposed to see that graph yet. Use a right Riemann sum indicated by the data in the table to approximate the value of 1 over 6 times the definite integral from 0 to 6 of c of t dt. Using correct units, explain the meaning of that integral in the context of the problem. All right, so probably the easiest way to visualize what the heck is going on here is to actually make a little scatter plot here. Let me visualize what's going on with the graph that you were seeing earlier. So here's a little scatter plot. If you do this on the test, it doesn't have to be to this detail. You just have something that you can very easily draw your rectangles with. Now, as far as this goes, if it's a right Riemann sum, we're not going to use the first left endpoint, which is 0, but we will use the last right endpoint, which is the 14.5 at 6. So our first rectangle is going to have a height of 5.3. It's the second dot that's in the picture there. So here's a sample graph or whatever. You don't actually have to come up with that. We just want each one of these rectangles. See how tastefully they're colored in a kind of coffee colored? I did that for you. Yeah. So if I wanted to calculate the Riemann sum, this right Riemann sum here, I'm just doing the lengths and the widths of each one of these, and you can see that the width, the delta x, on each one of these rectangles is exactly the same. It's just 1 unit wide, right? And then each one of the heights are, the first height is at 5.3, then 8.8, then 11.2, and so on, all the way up to 14.5. So if I were going to actually calculate the value of this definite integral, maybe I should choose a brown color here too. Okay, so this is this warm-up question. I've got 1/6 times the definite integral from 0 to 6 of c of t dt. Using a right Riemann sum, we know that we need to have like this approximately equal sign here. I'm going to carry over the 1/6. Now, if they're looking for a right Riemann sum, if this is actually on the AP exam, they do want evidence of multiplying some sort of rectangles here. Right Riemann sum needs the function value multiplied times each one of the widths. And so my widths here were each 1. Delta x is equal to 1, which is convenient. Doesn't always work out that way. You just look at your table values right here and see what the widths are supposed to be changing by. If it's always 1, of course, you could factor that thing out. If it's not the same, then you just have to multiply by individual little heights, or widths, I should say. So the value of this should be 1/6 multiplied times, and now let's just take the areas of each one of these rectangles. So that's going to be a 5.3, there's the function value, times its width of 1. Plus the next function value is 8.8 times its width of 1, 11.2 times its width of 1. Fast forward as necessary through this part. If it totally bores you here, I've got 12.8 times 1, 13.8 times 1, and then finally 14. Because it's a right Riemann sum, I'm going to use the 14.5. Also times 1. It's essential. Okay. Now, remember that, just kind of a recap here. A Riemann sum, this is going to look bad, so maybe choose green. A Riemann sum includes two things. It includes heights that are function values, which is the 5.3, the 8.8, and so on, multiplied times the width of that partition. And in each of these cases, that's the numbers in the parentheses. That's the 1, the 1, the 1, the 1, the 1. Okay, so now simplifying this guy, we've got 1/6 times, all the 1's, of course, are going to disappear because it doesn't do anything. Math. And 13.8 and 14.5. And this problem looks real familiar, right? It looks exactly like what we just did here. We just put the 6 down here on the bottom, so we know that this thing is supposed to be equal to 11.067. Now, as far as the units go, the C of t is in ounces. The dt t is being measured in minutes, just like we can see right up here. It's being measured in minutes. So times minutes. Now the 6 that's down here at the bottom, this is your 6 minus 0. Those are your 2 time values here. So this is actually in minutes as well. And you can see that the minutes cancel and gives us ounces back. So what the heck did we just find whenever we found 1/6 times the definite integral from 0 to 6 of c of t dt? We found the average amount of coffee that is in, what is this, coffee cup, right? Average, it's not through a filter, right? In the cup, yeah. So it's the average number of ounces of coffee in the cup over the time interval from 0 to 6. I'm going to go ahead and write this down. So 1/6 definite integral from 0 to 6 c of t dt represents the average value or the average amount of coffee. In ounces. In the coffee cup. Over the time interval from 0 to 6. I think it's in minutes, right? In minutes? Yeah, minutes. All right, there you go. So that's a perfect explanation of what just happened here. And it's also a fantastic introduction to how it is that we're going to find the average value of a particular function. Now, this one was with a Riemann sum so that we can actually visualize how it happens, and we could very easily tie it into just taking the average value of 6 individual numbers. But now, what we're going to want to do is take the average value of an infinite number of values of a continuous function. So that's what our objective is, being able to find the average value of a function. And you can see in this picture here, we've got ourselves a function, and then for some reason, we've got some sort of rectangle that's taken up some sort of space inside here. And why is there this like red dot where the rectangle hits the graph? I don't know. Maybe it has something to do with what we're about to do. Okay, so I'm going to show you in this part of the lesson exactly how you can find the average value of an infinite number of items. So to find the average value of an infinite number of items over, let's say, some sort of continuous function, you first have to partition your interval, for your closed interval from A to B. And we're doing our partition just like we did whenever we were talking about the area, and we define a definite integral, right? So delta x is equal to this b minus a over n. It's a regular partition. X sub I star, or if you prefer x sub I, is any value, any x value in the ith subinterval, right? So I pick, it could be the left endpoint, it could be the right endpoint, the midpoint, or any point in between any of those two, okay? So would you agree that if I were to just take any of these, I would take each one of those function values, so here's x sub I, or x sub 1 star, plus x sub 2 star, the function values of each one of those. I've got any of these, so I'm going to divide it by n. All right, so that's essentially what we just did on that Riemann sum question, because we had a finite number of them. We only had 6 of them to do. All right, so I can write that thing in summation notation because we have a sum of a whole bunch of things. So here's what it looks like. Is this technically a Riemann sum? It technically is not a Riemann sum because all we have is a function value and we don't have a width. So to make it a Riemann sum, we need to multiply it by a fancy 1. So here's the fancy 1 that we're going to multiply by. And it's almost exactly what we needed. And we're going to take the n that's on the outside of that, and we're going to replace it with the b minus a that's on the inside, the bottom one, and leave the top one there, right? We're just going to switch positions with those two things because it's all multiplication here, which is totally fine. Boop. And so here's what this thing is going to look like. And the reason why I rearranged it right there is because b minus a over n is the same thing as delta x, and now we have ourselves a Riemann sum. And if I take the limit as n approaches infinity of that Riemann sum, then I'm going to get a definite integral. And so here I have a way to find the average value of a particular function, a continuous function, over the closed interval from b to a, or from a to b. And you can see that the has a little fraction right up front, which is 1 over b minus a, which is the same thing that we had. It was a 1/6 on that coffee question that was that the whole lesson kind of was warmed up by. All right, so here then is going to be, for your notes, the formal definition of the average value of a function. If f is integrable on the closed interval from a to b, then the average value of your function f on that closed interval is given by the definite integral. Well, first, the fraction right up front, 1 over b minus a times the definite integral from a to b of f of x dx. So anytime you have one of these kind of problems, of course, you're going to have that little fraction that's right up in front. You have some sort of fraction there multiplying times a definite integral, cluing you into the fact that this is supposed to be some sort of average value, right? And so here in the picture, you see that there's this function, this black function here that's f of x, and the average value is represented, I don't know, like it's this line that's the top of the rectangle that's right there from A to B. And it does trace out some sort of rectangle, and we'll see what the heck that rectangle has to do with anything further on the lesson, the second part of this lesson. Okay, and here's another picture of this. And this one just has the line here. This line, something a little bit less than 5, represents the average value of this blue function of the closed interval from 0 to 24, let's say. All right, so that concludes the first video here. The next one is going to introduce some examples we're going to go through and actually find the average value of some of these functions.